Dr. Ming Dong from Syracuse University. Occupant-Centric Ecosystems, from Smart Buildings to Smart Cities.
Good afternoon, everyone. It's last talk. I hope everybody still can awake. So I totally from different background, from civil engineering. So I'm a professor from mechanical and aerospace engineering, also affiliate professor from civil environmental engineering at Syracuse University. I'm also a associate director for New York State Center of Excellence in Environmental Energy System. So today I'm going to talk about a very interesting topic that I think nobody mentioned this before in all the engineering design, resilience design system, which is occupant behavior. So we know that through our studies of urban mobility, GPS logs in Lower Manhattan, we found out people spend over 90% of time indoors. People transition from different buildings, homes, work locations, grocery stores, or different buildings, but they spend 90% time indoors. And this is often a missing piece when we think about urban infrastructure system. So when we design urban system, we talk about power system, buildings, bridges, food supplies, water systems. But how many times think about was the behavior of people in those urban infrastructure systems? And the behavior of people actually decides the system demand, right? And all the purpose of those power, water, building are for the purpose of people living healthy and have a good indoor environment in the buildings. So have a very interesting example, a very simple example that temperature set point in most commercial buildings is scheduled. However, the actual occupant behavior is dynamic, and nobody will change the temperature set point to track the occupant dynamic behaviors because we don't have that sensor. And even we have a CO2 sensor, it cannot have a good indication. And now often we have a motion sensor, but motion sensor cannot tell how many people are in the space. For example, it cannot tell how many people in this conference room so that you can control the outdoor air intake. So slowly, occupant behavior become a leading factor. So the question, research question has two. The first one is, does human behave as we expected when we design the complex system, like resilience, mitigation strategies, fit this workshop's topic, HVAC controls, building retrofits. Next question is, what's the impact of human behavior on those engineering system design and operation? Like inefficiency, great flexibility, resilient building design, what are the impacts? So we started with very simple behavior in one building. So the challenge of occupant behavior in one building is we want to know 4 questions. Is this space occupied? And how many people in the space? When the space status in next 24 hours, if we can predict. And what is first arrival and the last departure time of occupancy. And this is always behavior driven. And this behavior could be depending on the time of the day, could be depending on the building type, environmental conditions, and also occupant itself, which is also social, physiological, psychological impacts on those behavior. So ultimately, it's a very stochastic and dynamic system to understand people's behavior in and out of the building. So starting 2007, we starting to collect those behavior data in office buildings, residential homes, in low-income homes, hotels, and office buildings, and student dorms. And we also have actually also funded a project called a Global Occupant Behavior Database. So we work with people from 15 countries and 32 universities together to have 32 different datasets to cross the global and collect data from different building types to understand people's behavior. And there's, this database is open, and you can download data from the obdatabase.com. So I use one example collected in Syracuse. So this example the goal is example is to do a net zero energy retrofit for a student dorms, and there are 16 student dorms, and energy retrofits is very common for the older buildings, and this will involve architects, civil engineers, right? So basically, we want to want to install the PVs, want to install the heat pump system, and make sure the overall energy generation of the year is net zero, right? So it's a simple problem. However, when we start to think about this, look at this retrofit problem, we found something is challenging. So we installed the indoor air quality monitoring. We installed the door and window contact sensors. There's operable windows in the living room and the bedroom. And also we installed the power metering to understand basic electricity usage. So first of all, what we found out is out of these 16 student dorms, none of the dorms have the same electricity usage pattern. Every dorm is different of these 16 dorms, okay? And this is disaster when you build an energy model, try to look at what kind of retrofit strategy you want to do it, because you have to calculate this 16 dorms one by one. And then the second one is we found out the behavior of people opening the window. So the student will open the window in very cold winter when outside is minus 20 degrees C. So x-axis is the degree C instead of degree F. And then they also can open the window at very hot summer, which is outside 30 degrees C, right? So what's going on? Okay, and when they open the window, of course, the HVAC energy, right? Especially in the winter time, the heating is suddenly jumping because they open the window. So then we look at what's going on exactly. This is when outdoor temperature is negative 10 degrees C. Students open the window because indoor TVOC is too high. So there's very bad indoor air quality. So they open the window. So once they open the window, the indoor temperature decreases from 20 degrees C to 10. And that immediately triggers high, energy consumption on the HVAC system. So that's one of the reasons, right? It's not because indoor temperature, it's because indoor environment quality, right? So based on that, so we want to look at what's the impact of OB on the occupant behavior on HVAC energy consumption. So we build deep learning models to predict window opening behavior based on the indoor-outdoor conditions in indoor environment as well. And then as input into the energy plus model, and then energy plus model can predict how much energy consumption for the HVAC system. So what we found out is if we consider the occupant behavior, the HVAC system energy consumption is much higher than if we don't consider the behavior of the people, especially window opening, and also don't consider the dynamic occupancy in and out of the dorms, right? So, but in the practice, in the real practice, people always set a default schedule for the occupancy, which actually underestimate the energy consumptions of HVAC system. So when you do the retrofit decisions, which profile you will base on, right? There's a big question mark. So I use this very simple example to illustrate occupant behavior is very important when you make design decisions. So now let's look at how we, from the building level to the urban scale. So at urban scale, it's more complex, right? At building level, you can measure each building. You can put sensors at the building and measure it. But urban scale is difficult. So people often use a tool called Urban Scale Building Energy Monitoring Tool. Like the CDBS from Airbnb or UMI tools from Harvard. So to look at urban scale energy consumption, the purpose is to urban scale planning or the building design. So, but there's one assumption for the occupant behavior. Either people use time use survey data and build AEMS models, do the Monte Carlo subpooling to generate occupancy schedules for each building, or you just use the default schedule for any plus, which is ASHRAE standard. So ASHRAE standard 90.1 defines the occupancy schedule for 16 different type of buildings. Okay. And then what people often do is just use default occupancy schedule in the N plus, which is defined by ASHRAE, as input into those urban scale building energy modeling tools. Okay? which is free. It's different from actual, right? So, but what I want to say is location-based social media data is available. So there's a lot of Twitter tag data, there's cubic GPS data, there's Facebook gene data, place data, and traffic data, and also Google Street View data. So how we can utilize those big data? So in our group, we use cubic GPS data. So look at urban scale home mobility. So mobility data is a vast amount. So this is showing an example of raw GPS data in Arizona. Every hour, there's 1 million rows of data, and with 11,000 unique users. Okay, so every 1 hour. So we have 1 year data, and you can imagine how many millions rows data we have to process for the Arizona, Phoenix area. So for the human data, what we can get? So we can get spatial temporal track of the people. So we know exactly what time, when, where people is, and we can classify their home locations, work locations, and other locations. We can also understand how long people stay in this location. We call it stay duration, right? Well, there's a series of methodology that can extract the stay locations, home locations from the GPS data, which I will not talk about here. So we also, based on those different locations, we also build the LSTM models to predict next, like say 12 hours, when these people will be, which building, which location will be, right? And then we reached, for this example, reached 85% accuracy. And the next diagram is showing like over the 93,000 users, 3 months data, we predict everybody, right? Build up 93,000 LSTM models, because everyone's different, and predicts 93,000 users, and the overall accuracy is pretty good. It's reached 83%. So looks like we can actually use mobility data to do something, right? At least to predict location of the people. But there's challenges of the human mobility data. So the first challenge is sparse. So data very sparse. It only represents 20% population of coverage. It does not represent 100%. And that's how they collect the data. And then the second one is it may not cover all building types in the urban area. So it may only cover a few types of buildings. And then the next challenge is discontinuity. So the data may not continuous temporally and spatially, right? Sometimes the user will not have data for 1 day or 2, and then suddenly there's data come out, right? So the data is not continuous. So what we can do? So how we can model occupancy at urban scale more effectively? So we come out a framework called a fit-for-purpose framework for the urban occupancy modeling. So in this framework, we look at so-called level details. When we try to do the urban scale energy modeling, what is the ideal case? The ideal case is I understand everybody's movement and behavior, and understand at what time when people A will be at which place, which building. So what you can do is you can for each building, you can aggregate. You can understand the actual schedule of this building A, right? However, we don't have this data, right? So then what people do is, okay, how about we call a deterministic model? So we group the buildings, right? So if there's all office buildings, we get the average profile, okay? And then we can also have individual buildings, right? Instead of group buildings, we have a probabilistic models to generate the individual buildings profile. Or we can also look at personalized level, as I said. So I don't look at the building level, but I look at personalized level. At a personalized level, I can also group the occupants. So a group of people represents the same behavior. So we can use time series K clustering method to cluster those people first, and then create a schedule for this group of people. Or the last model is LOD P1 is individual occupancy. Like I said, is most comprehensive behavior. So from this, what we did is we use GPS data, and also because in order to generate 100% data set, we use STM GAN model to which is generative AI model to generate the data for the whole population of a certain area. And then for each of the method level details, we generate different schedules and look at how those schedules will impact the ultimate results on the energy simulation. So this is how we convert from mobile data to the building occupant schedule. So we extract the state point of the mobility, and then we use inhomogeneous Markov chain models to create the state points in the different buildings, and then we use a spatial joint. So if the state point is within the spatial joint, that means the people is in this building. So we can come out with building schedules. And this is the results of the generated occupant schedule. So we compare with measured and simulated data, and we use 3 indicators: GS divergence, KL divergence, and FID score to judge if our GAN generates the data is actual aligned with realistic data. And actually it is, and the GS and KL divergence score is very low. So we can have confidence that our generated data actually represents actual situation, what's happening. So this is 3 diagrams showing the people's arrival time, people's departure time, and also the origin time in the one building type. So then we look at how different data sources influence occupancy modeling. So as I said, there's different data sources when you create occupant schedule. So you can get the occupant schedule from the standards, right? So from the ASHRAE standards, from the enterprise models, there's a well-defined schedules for different building types. You can also get occupancy schedules from the survey data, which is normally is ATUS data, American Time User Survey data. And then you can get the open schedule from GPS data, or you can get schedule from the synthetic data, which is GAN generate data. So we compare those different schedules. This is the overall average schedules with the ground truth. So we're using the same modeling method in homogeneous Markov chain modeling for individual occupants, and then the population coverage. Of course, the standards cover different building types, but the GAN data cannot cover all the buildings, but it covers some of them. So GPS data cover less, and survey data cover much less. In terms of accuracy, we found GAN data is much more accurate than GPS data, than the survey data and the standards. And then, so from here, you can be give us a caution that when you do the urban scale energy modeling, what kind of the occupancy schedule you use, right? Which schedule you come from? Because those schedules could give you a different results on the urban scale energy modeling. So the next one is how the model formalization influence occupant modeling, right? So in this case, we're using the same data source, but using different modeling method, right? It could be an individual Monte Carlo inhomogeneous Markov model. You could aggregate the Monte Carlo model into the one, or you can do a clustering first, and then you create a different models, right? And then the last one is the standards. So this also give you different occupancy schedules as well. Now let's look at what's impact on the district energy simulation. So we use the peak energy usage as KPI, and we model 779 buildings. It has 6 building types. They have residential, community area, shopping plaza, and a campus. 779 buildings altogether. Those buildings are created in the Energy Plus, so there's 779 Energy Plus models. But with different schedules, each building has different individual schedules. So what we found out is compared to the ground truth data, the determinant schedule has most difference, right? It's up to 20%. And then if you use individualized, very detailed individualized schedule, which is LOD P1 and LOD P0 These are personal-based schedules. You have a lot of computational complexity because you have to model each people and then you aggregate those people into those 779 buildings. So it gave you high accuracy, but it's more computational complexity. So the middle point is really using the LOD-S2, which give you relative small error, but it also have much less complexity. So the next question, so after we have all these results from open scale occupancy modeling, so the next question is what's the impact of human behavior on engineering system design and operation, right? So what if we know the occupant behavior, how this will impact the engineering system design operation, especially on the building design, on the energy efficiency, and also grid flexibility, right? So I will present one problem which we didn't mention in the resilience, which is power outage. So power outage is getting more and more common because we have increasing PV and EV usage, especially in California. So PV will have a potential overgeneration but in the daytime. So when you have overgeneration happen, then will cause blackout of the power grid. And this is we need to design some resilience strategy to avoid that, right? And also when you have a lot of PV, then the grid management have become complex because it need to have a huge jump of the power generation after the sunset. Okay, it's really that. So then another challenge is increasing EV adoption will bring more challenge to the grid management, right? So this is a report in 2022. There's a prediction by 2050, there's 1 billion PV will be running on the road, right? And imagine, like say, 1 billion PV, plug into the grid, charge it during daytime or nighttime. It will bring a lot of challenge to the grid management, right? Grid is already very headache with the PV generation, and then you plus EV, and EV usage is really depend on the people, right? It's really tied with people's behavior. So what we can do? So this is one project sponsored by NSF and working with APRI and SRP. So we look at 17 years data of smart meter data, and looking at how the adoption of the DERs by both PV and battery systems. And we compare the energy usage of individual houses before and after install the PV battery. So what we found is a very interesting rebound effect, right? So some months, so the blue line is before the PV installation, and the orange line is after. So I circled the months January and February. So some months the peak is increased, right? So especially the peak is after sunset. So in people starting to using a lot of electricity after they install the PV and battery system because they think PV is free. So that's why they open the light, don't turn it off, or they turn on some devices, never turn it off because they think it's free. Right? So it's called typical rebound effect, okay, in the social science. So based on that, we try to develop human mobility-driven, large-scale EV controls. So we look at where and when to charge and discharge EV system to minimize the cost, also balance the grid stability based on human mobility. Okay? Because imagine that everybody controls their EV, and also I want to charge whenever I can. Then in the future, when there's a lot of EVs on the grid, right? So the grid will lose management and it will cause blackout. So we develop a framework. It's called a vehicle to building to grid integration framework. So we look at some mobility. We specifically try to understand when where the EV will go and how long the EV running on the road each day, and when we can charge and discharge the EV. And also we look at PV generation at home, battery adoption at homes. For those homes, we have a PV battery system. and we built a model of the buildings, the PV system, battery system, EV system, and also building models. When I say models, it's mathematical models for the power distribution and generation, and put them together into operating framework. So specifically on the urban scale human mobility pattern part, we extract travel distance, arrival, departure time for both homes and work locations. And we use the EV battery as a flexible resource to support building and grid usage, right? And so the graph showing the distribution of the arrival time and departure time in the home, and also arrival time, departure time in the workplace. And then the right side is showing the average duration of the people, duration of people at travel distance across the different users. And then we use Enterprise as a modeling platform. So we actually simulate a real community in Phoenix area in Arizona. And this is actual community. And we replace each building with DoD prototype residential buildings and simulate every building in this community. And each building will have a customized occupancy and HVAC set-point schedules derived from the human data. And then what we did is we compare 3 different cases. The case 1 is what people often do is reducing users' cost. So we don't consider anything from the user point of view. I want to have minimum utility bill as much as possible, especially if I can pay nothing for utility companies, right? So case 2 is we balance reduction with users' cost and greater stability, right? And case 3, we're reducing the total building energy demand. Okay, there's 3 different cases compared to 3 different control strategies. So let's look at case 1. So if we want to only reducing the user's cost, there's many things you can do, right? So you can do a load shift, which is actually load shift happening from the daytime to nighttime. But we have overgeneration risk, right? And then there's also there's a load shift. And then we also have increased peak demand because you shift too much load. And then when after sunset, you try to catch up. So you increase the peak demand, okay? And then there's the overgeneration as well. So if we only want to reducing the user's cost as much as possible, then it's very bad to grid because you have a larger load shift. You also have overgeneration risk, right? So which will cause a great blackout. So if you look at case 2, so case 2 is you balance the greater stability, and also you look at reducing the utility bills on users. So it's a totally flat curve. So there's no overgeneration, no increase in peak demand. It's as flat as possible for the overall 1 day. And we're also running the more cases, and this is normalized the net load profile. I can see in case 2, the fluctuation reduced by 74% compared to the case 0, right? But the other cases, case 1 and case 3, if we don't consider the greater stability, then you can see the load fluctuate a lot in the daytime, which will potentially cause a blackout of the power grid. Okay, so last case I talk about is how we can consider occupant behavior adaptation on the disrupt event or extreme event, right? For example, what if the power grid outage happened already, right? How we can how the behavior adaptation will impact the mitigation strategies. So in this case, I use PV battery system sizing as an example, right? So what often people do is have a microgrid, which including the PV and battery system, or we call nanogrid, each home. And when there's a power outage, then the battery will turn on, right? And then the question is, okay, how we can sizing the battery? Of course, when you have infinite money, you can buy as much as possible. How big the battery is, right? You can buy a big battery that lasts for 3 days, right? But we have constraints on the budget, on the financial, right? So there's a balance between the resilience and the sufficiency. So resilience means, sufficiency means you want the people, how much energy is enough for people to survive. Okay, that's called sufficiency. That's a new concept. And resilience, of course, means I think everyone understands what in this case means how long you can stay in without a power outage, right? That's called resilience. So we consider three factors. The first factor is called mobility adaptation. So what is mobility adaptation? So it means occupants are willing to temporarily relocate during the disrupt event. So for example, if my home, there's power outage in my home, I can spend another 2 hours in my friend's home where there's still power on, right? There's no outage, okay? So that's called a mobility adaptation. There's a probability on that. And then the second one is called a comfort adaptation. So if there's a power, if there's no power outage, I can set my temperature set point to 72, right? But if there's power outage, I can, put the temperature. You cannot change the temperature at all. So you can stay at home until temperature reach 85, right? Sometime, I don't know. So in Texas, when I live in Texas, my utility company is CPS Energy. So I sign up. So they call it demand response program. So when outside 120 degree F and inside 85 degree F, they shut down my AC. I cannot turn it on on my AC. So, but I can still survive for 30 minutes. So after 30 minutes, I call them to complain, and then they allow me to turn on my AC. Right? So under 35 degree, I turn on my fan. I wear less. I drink a lot of water. It's called a comfort adaptation, right, for 30 minutes. So the last one is called activity adaptation. So occupancy change activities during disrupt events, right? So maybe you cannot watch TV. You probably if you have battery system, you probably do only keep the refrigerator on for a while, right? So you don't watch TV, right? Or you don't do laundry or dishwasher since you wash by hand, right? Even you have a battery, right? You want your battery to last longer. So those are three behavior adaptations, right? And then based on that, we create 6 cases. And these 6 cases is based on the 3 adaptations. And then we sample these cases, we put into the enterprise simulation, we generate so-called critical load. So critical load means how much required load you needed during the power outage so that you can size in your battery and PV correctly. Okay, so based on the critical load, then we try to size in the PV battery system. It's an optimization problem. And this is interesting 6 scenarios. So there's a 1 day in Atlanta. And so the black line is the baseline, which means I just want to use everything I want, right? So of course, the critical load is much higher. So then what we found out is the critical load can be reduced by activity adaptation, the comfort adaptation, and also mobility adaptation. So these things can be actually reduce your size of the battery and PV system. Okay, so based on that, we did some impact of behavior adaptation and system sizing of across the U.S. different climate zones, and we interestingly found out the PV can reduce 85% capacity observed in Miami, and then the battery capacity can be reduced by 68.9% in Phoenix. So as a conclusion, I always think it's all about human behavior, right? So in the conclusion, I have one example is on September 7th, 2022, California experienced an extreme hot heat wave event. That's if everybody turn on AC, it will cause blackout for sure. So then California CASL sent out a text message to everybody, say, please turn off your AC. Okay, in 5 minutes, 400 megawatt hour power was shedded in 5 minutes. Okay, and in another 20 minutes, 2,000 megawatt hour power was shedded in 20 minutes. So you can see the power of social response, right? You can see the power of human behavior. So it's all about human behavior. Right? If we can change our behavior, we can save our planet. So I want to acknowledge my lab members, PhD students, myself, and we are at Syracuse Center of Excellence building in the Environmental Energy Systems. It's a 5-story, 55,000 square footage platinum building with 16 labs and test beds. You are welcome to visit us. Thank you.
All right, thank you very much.